I am certain everybody remembers the fixed support when we talked about support reaction and when we defined the 3 different support types. So right now we only have to refresh them. Let's talk about fixed supports, and they can be represented in different ways. One of the most common one is probably with the line through the wall, as I do it here, but sometimes you also see them, for example, in a different way. So let me draw that. So sometimes you also see them as such. And it doesn't really matter how you do it as long as you understand what the purpose of this symbol is. And the most important one that we remember is that we needed 3 conditions to be true for our systems so that they can support forces. And what were those conditions? We said that the sum of the forces in the x direction must be equal to 0. The sum of the forces in the y direction must be equal to 0. But also the sum of the moments about any point must be equal to 0. Now, what that means in terms of a cantilever beam, and you can think of this as a balcony, right? The balcony that you probably have in your apartment complex or wherever you currently are. I'm sure you can find a balcony somewhere around you. You can see that there's only one support and not, as we had before, 2 types of support at A and B. So here we only have a support at A. And that support now needs to prevent these 3 things all in one. And that's why the free body diagram for this type of support looks slightly different. Keep in mind that the picture that you see above here is not a free body diagram. A free body diagram has the forces in it. And so the forces that I need is I need something that prevents vertical motion. I need something that prevents horizontal motion. And we usually call those, let's say, RAY and RAX. But we also need this third condition to be true, which before we always solved by putting another support here. That was a simply supported beam. Now we cannot do that. We have a cantilever beam. So that means what this support has to offer is a rotational resistance, right? So we need something here, which we usually call M at A about the z-axis. And so you can see that if you provide this, the system does not fall down, it does not move left and right, and it does not rotate. And that is important for our static systems so that they actually remain stable. And all these 3 conditions have to be met. Without that, it does not work. And why am I saying this so repetitively? Because often I see students look at these structures and then they find RAX, they find RAY, but they don't find the moment. And that's actually the most important one. And probably it's also an easy one to find because you do not have to deal with unknowns anywhere else than at this location. So the only unknowns in your system are usually at this one support, and that makes your life very easy and very fun. So let's look at that, how that is implemented. For example, if I were to place a self weight on there, so let's pretend that this here has a self weight and I use just, let's say, 10 newtons, so 10 newton per meter. And let's make our life easy and let's make it, 4 meters long. So 4 meters long. Then what I would do is I would calculate, let's say, my RAX first, and I would do that by the sum of the forces in the x direction being equal to 0. And of course you find that 0 is equal to RAX. And I don't have to worry about that anymore, but it is still a result because there could be a horizontal force on there. Now, RAY is very simple to calculate because you only will end up with one unknown, as I said. So the sum of the forces in the y direction is equal to 0, upwards positive. By the way, here I should indicate that too. And 0 is equal to, and I assumed this to go upwards, which makes sense, of course. So plus RAY minus 10 Newton per meter multiplied by 4 meters. And be careful now, because remember what I said earlier, sometimes students confuse things when it comes to these units. So here we have 10 newtons per meter and multiply it by 4 meter, and that goes hand in hand with what we have here. So now we only have a force here, and Newton per meter multiplied by meter is a force. So therefore, this equation is already complete, and we would find that RAY is actually equal to, careful, plus 40 Newton. And that is what we want. We want a force, right? So this is an answer. And now we are left with the last unknown. And the last unknown would be MA. So MA, I now find this, and this is the first time you see this, I find this by taking the sum of the moments about any point, right? Remember, I can always take the sum of the moments about any point. If the system is not rotating, if this system does not rotate, then I can take the sum of the moments about this point, this point, this point, this point, this point. It doesn't really matter. But the smartest point to take is probably this point, because then I don't have to include RAY into my equation. And actually also not RAX. If I were to take about, let's say, this point, then I would have to include this and this. And I want to avoid that, so I take the sum of the moments about point A. So let's go ahead and do that and say that is equal to 0, counterclockwise positive, and 0 is equal to, and I start with my unknown as always, MAZ. I assumed it here to turn counterclockwise. That makes it positive according to my definition, so plus MAZ. And now I need to find the lumped force there of this system, so 10 Newton times 4 meters, and then it has a lever arm of 2 meters, which then rotates clockwise. Therefore, that is negative. So let's say minus 10 Newton per meter multiplied by 4 meters. And remember where that is acting. It acts exactly in the center, so multiplied by 2 meters. And just because we're still learning this, this is the F resultant, or the lumped force, and this is the lever arm. And this, by the way, is the rotational sense. So please keep that in mind. And I want you to pay close attention to this again. You have to take, you don't have to, but it is so much better to take the sum of the moments about this point where MA is acting when you find the support reactions. If you do that, you will be very thankful later on when we move into internal forces for reasons that I cannot explain right now, but you will understand them when we get to internal forces. However, if you do that, it will be very helpful for you, and you should memorize this. Always take the sum of the moments about that point where the cantilever is supported, so that you can actually use this equation where RAY and RAX does not influence this equation. Nevertheless, we can now calculate actually that our MA, so MA is actually equal to what? 40 times 2, and that is actually positive. So plus 80 Newton meters. This is also important to understand, right? So it's a moment that we're calculating. Therefore, it needs to be in the units of a moment. And we have that because this cancels out this, but the other distance remains, the other m remains. And you understand that we need to end up with a force times lever arm. Also important is this positive here. What does the positive tell me? Similar to what we talked about in the last lecture, this positive does not necessarily tell me that it's clockwise or counterclockwise. It just tells me that I assumed this direction correctly. And this can be confusing sometimes because so often the plus here coincides with this being counterclockwise. But that is only true because I defined it as such. Really, you need to read these pluses for your support reactions as, hey, either I was right, plus, or I was wrong, then it would be negative, right? So what this plus means is you interpreted the direction correctly. For example, if I had assumed MAZ to go in this direction, what would have happened? Then I would have ended up with a minus MAZ in this equation here. And then I would have found that I end up with a negative here, right? So then this would be negative 80. And I encourage you to really think about this if you understand this, how this equation would affect this to be negative. And when that is negative, then I would say, hey, it's not turning clockwise. It actually means I assumed this arrowhead incorrectly, therefore I need to turn it around. So please understand that this tells you being right or wrong. It does not tell you clockwise or counterclockwise. It's a common misunderstanding because we have defined it here as such, and students have not enough experience in the beginning to understand the difference between the clockwise, counterclockwise versus correct assumption and incorrect assumption. But take my word for it, this plus only tells you that you assumed correct. For this part here, you would have found that you assumed incorrectly, and therefore you would have to reverse your logic. But to sum up the fixed support refresher here, please understand that we have 3 support reactions that are symbolized by this little symbol with the 3 lines that are diagonal. And also notice that there's no circle here, so it's kind of clamped in. In fact, the way you can represent or think of this is take a pencil in your hand and don't let it fall down. Take it in one hand and you pretty much perform the action that the wall usually performs on the balcony, right? So this clamps this beam, and because it clamps, you don't just have the vertical and the horizontal force, you also have the rotational force. And that guarantees that all these 3 equations can be satisfied by just one support reaction. And that gets us ready for our examples, and we can now go ahead and solve cantilever problems with distributed forces on them.